Welcome to this EWRB Electrician Theory Exam Training course. I'm Aria, an electrical tutor working with EWRB. In this course, I'll guide you through all the topics covered in the EWRB Electrician Theory Exam Teaching Guidelines. Welcome back. Today we are learning topic 13, Electrical Protection, which is one of the biggest and most important topics in the electrician theory syllabus. This topic is all about keeping people, equipment, and property safe from electrical faults. We'll look at what excess current is, why it's dangerous, the different types of protection devices, and a long list of terms every electrician must understand. Then we'll cover residual current devices, RCDs, in detail, including types, classifications, requirements and AS/NZS 3000, maximum trip currents from the ESRs, and testing methods. Finally, we'll move on to isolating transformers, their principles, their safe use, and why they are rated in kVAR rather than kW. There is a lot to cover here, so I'll take it slowly and clearly. Let's begin. 13.1 Protection. 13.1 is state what is meant by the terms rated current and excess current protection. Rated current is the maximum continuous current a device or cable can safely carry without overheating or being damaged. Excess current protection means using devices like fuses or circuit breakers to stop the current from rising above that safe level. When too much current flows, the device disconnects the supply to prevent overheating, fire, or equipment failure. 13.1b describe the danger of excess current to cables and equipment. Excess current heats up cables and equipment. If the current is too high, the insulation softens, melts, or carbonizes. Once insulation breaks down, metal parts can become live, starting fires or causing shocks. Equipment can burn out or fail internally. Excess current is one of the biggest causes of electrical fires, which is why correct protection is essential. 13.1c state forms of excess current protection, close excess current protection, coarse excess current protection. There are two forms of excess current protection, close and coarse. Close excess current protection is the more sensitive type. It will operate within 4 hours when the current reaches 1.5 times the designed load current of the circuit. This means the protective device responds sooner when the current is above normal levels. Close protection is found in modern protective devices such as MCBs and HRC fuses. Coarse excess current protection is less sensitive. It will not operate within 4 hours at 1.5 times the designed load current. This protection operates much later under moderate overcurrent levels and is mainly associated with older devices such as rewirable fuses. Rewirable fuses were common in older homes, but AS/NZS 3000 does not allow rewirable fuses to be installed in new installations in New Zealand. They may remain in older systems but cannot be used for new work. So the difference is simple. Close protection equals operates within 4 hours at 1.5 times design current. Coarse protection equals does not operate within 4 hours at 1.5 times design current. That is the full distinction between the two of excess current protection. 13.1d explain the following terms applicable to sub-circuit protection: voltage rating, current rating, utilization categories, breaking capacity and kVAR rating. Voltage rating is the highest voltage a protective device can safely withstand without flashover. Current rating is the maximum current it can carry continuously without overheating. Utilization categories describe how the device behaves with different loads, for example, general loads or motor loads. Breaking capacity, or car rating, is the maximum fault current the device can safely interrupt. The kVAR rating links to the supply fault level and tells us how much energy the device must withstand. 13.1e describe the construction, operation and applications of semi-enclosed rewirable fuses, HRC fuses, miniature circuit breakers, cartridge fuses, fusible links, magnetic overload relays, thermal overload relays. A semi-enclosed rewirable fuse uses fuse wire that melts under overcurrent, simple but coarse protection. HRC fuses are sealed with a calibrated element and sand filler, giving fast and safe interruption at very high fault currents. MCBs use thermal and magnetic mechanisms to trip on overloads and short circuits and can be reset. Cartridge fuses are sealed one-time fuses used in appliances or control gear. Fusible links melt at high temperatures and protect heating appliances. Magnetic overload relays use a solenoid that trips instantly on heavy overloads, often with time delay. Thermal overload relays use a bimetal strip that bends as it heats, tripping the circuit at sustained overloads. 13.1F Understand and explain the following terms. Current rating, voltage rating, fusing current utilization category, tripping factor, cutoff characteristic time versus current characteristic category of duty, discrimination, backup protection, rupturing capacity, prospective short circuit current, sensitivity, earth fault loop impedance. Current rating is the safe continuous current the device can carry. Voltage rating is the highest safe operating voltage. Fusing current is the minimum current needed to melt a fuse. Utilization categories describe application types, such as general or motor loads. Tripping factor is how much current above the rating will trip an MCB. Cutoff characteristic shows how fast a device stops rising fault current. Time current characteristic shows trip time at different fault currents. Category of duty describes voltage and braking capacity combinations. Discrimination means only the nearest protective device trips during a fault. Backup protection uses a higher rated device upstream to handle large fault currents. Rupturing capacity is the maximum fault current the device can safely break. Prospective short circuit current is the highest fault current available at a point. Sensitivity is the imbalance current level that makes an RCD trip. For example, a 30 mA RCD often trips earlier, around 18 to 22 mA. So sensitivity tells you how small the leakage current needs to be before the RCD disconnects. Earth fault loop impedance is the total resistance of the fault path when an active conductor touches an earthed part. Low loop impedance means high fault current and fast tripping. High loop impedance means slow or no tripping, which is unsafe. 3.2 Residual current devices, RCDs. 13.2 Understand that RCDs provide supplementary protection to users of electrical equipment. RCDs provide supplementary protection, which means they add an extra level of safety on top of fuses and MCBs. Fuses and MCBs only protect against overload and short-circuit currents. They do not trip when small leakage currents flow through a person. An RCD protects people by detecting very small leakage currents, usually 10 mA or 30 mA, that could pass through the human body. If any current leaks to earth, for example, through a person touching a faulty appliance, the RCD senses the imbalance and disconnects the power within milliseconds. This fast disconnection greatly reduces the chance of electric shock, muscle freeze, can't let go, burns, or ventricular fibrillation. So in simple terms, RCDs are designed to protect people, not equipment, and they do this by disconnecting the supply very quickly when even a small leakage current occurs. 13.2b Demonstrate knowledge of the maximum tripping current and operating times for RCDs to be deemed electrically unsafe. Regulation 24 tells us when an RCD is considered electrically unsafe. These rules apply to both fixed RCDs in installations and portable RCDs used with appliances. For a standard 30 mA RCD used for electric shock protection, it is unsafe if it fails any of the following. 1. It must trip within the required time at its rated current. It must disconnect all live conductors within 300 milliseconds at 30 mA. If it takes longer than 300 milliseconds, the RCD does not provide safe protection. 2. It must trip very quickly at 5 times its rated current at 150 mA. It must trip within 40 milliseconds. If it does not meet the 40 milliseconds requirement, it is unsafe. 3. It must not trip too early at low leakage current. The RCD must allow at least half of its rated residual current before tripping. So for a 30 mA RCD, It must not trip at 15 mA or below. If it trips too early, it fails regulation 24. 4. It must meet AS/NZS 3190 performance requirements if the RCD does not match the testing limits in AS/NZS 3190. It is electrically unsafe. 5. Additional rules for 10 mA RCDs for RCDs protecting children, AS/NZS 3000 mandatory situations, and medical patient locations. Rated current must not exceed 10 mA. Must trip within 40 milliseconds at rated current. Must trip within 40 milliseconds at 5 times rated current, 50 mA. Must not trip below 45% of rated current. So in simple terms, to be safe, an RCD must trip fast enough at the right leakage current, must not trip too early, and must meet the exact time current limits in Regulation 24. If it fails any of these tests, it is legally unsafe and must be replaced. 13.2c explain the checking and testing requirements to ensure that RCDs installed for protection against shock are Type A for New Zealand. In New Zealand, all RCDs used for personal protection must be Type A. Type A RCDs detect AC leakage and pulsating DC leakage, which is important because many modern appliances, such as induction cooktops, EV chargers, speed controllers, and switch mode power supplies, produce DC components that a Type AC RCD may not detect. When checking RCDs, we confirmed 3 things. 1. Correct type. The device must be clearly marked Type A or better. If the marking is unclear or missing, the RCD cannot be used for shock protection. 2. Correct installation. It must be wired correctly, supply connected to the right terminals, and all active conductors passed through the sensing coil. 3. Correct performance. Using an RCD tester testing a 30 mA RCD. A. Test at half times rated current, 15 mA, no trip. B. Test at rated current, 30 mA, must trip within 300 milliseconds. C. Test at 5 times rated current, 150 mA, trip within 40 milliseconds. D. Test at both 0 degrees and 180 degrees phase angles. If the RCD fails any test, it is electrically unsafe under Regulation 24 and must be replaced. 13.2d Understand the operating principles of an RCD. An RCD works by comparing the current in the active conductor with the current returning in the neutral. In a healthy circuit, these currents are equal. The RCD contains a toroidal core and a sensing coil. If some current leaks to earth, through a person, a metal frame, or damaged insulation, the active and neutral currents become unequal. This imbalance produces a small magnetic signal in the sensing coil. The RCD detects this instantly and trips the internal switch mechanism, disconnecting all live conductors. RCDs do not protect against overload or short-circuit faults. That is the job of MCBs and fuses. The RCD's purpose is purely shock protection, reducing touch voltage duration. 13.2e Be aware of how RCDs are classified. RCDs can be classified in several ways. Method of operation. Some RCDs work independently of supply voltage, electronic-free designs, while others require line voltage to power their sensing circuit. Type of operation. Types include AC, A, F, and B. Type A is required for NZ shock protection because it detects pulsating DC. Type B detects full DC and is used for EV chargers and specialized equipment. Number of poles and current paths. RCDs can be 2-pole, single-phase, or 4-pole, 3-phase. They must disconnect all live conductors, including neutral. Adjustable residual operating current. Some industrial RCDs allow their operating current to be adjusted, for example from 30 mA to 300 mA. Resistance to unwanted tripping from voltage surges. Better quality RCDs include filters to reduce nuisance tripping caused by lightning or switching surges. Behavior and presence of DC components. Type AC RCDs may be blinded by DC, so NZ requires Type A or better. Protection against external influence. RCDs must have suitable IP ratings and be mounted where physical damage or moisture is controlled. Method of mounting: DIN rail, socket outlet RCDs, SRCDs, portable RCDs, PRCDs, or fixed RCBOs. Method of connection: some require hard wiring, others plug-in or appliance integral types. 13.2F Understand the operational characteristics of RCD types and how different available RCDs operate, including RCCB, residual current circuit breaker, provides residual current protection only, no overload protection. RCBO, residual current breaker with overcurrent protection, combines RCD and MCB functions in a single device. This is the most common residential option. SRCD, socket residual current device, a socket outlet with built-in RCD protection. Often used where an RCD cannot be added to the switchboard. PRCD, portable RCD, used on construction sites, workshops, or with handheld tools. Protects the user even when the fixed installation lacks RCDs. Voltage-independent RCDs operate even when supply voltage is lost. Required for Type A shock protection in many situations. Voltage-dependent RCDs need supply voltage to power their internal electronics. Used mostly in PRCDs. Typical residual current ratings: 10 mA for high-risk areas, 30 mA for personal protection, 100 mA or 300 mA for fire protection. Classification relating to DC components: Type A responds to AC and pulsating DC, required in NZ. Type F and Type B handle more complex waveforms. Load leakage currents: all appliances leak a small amount of current. Circuits with many appliances may approach the RCD's trip threshold. This affects RCD selection and circuit grouping. 13.2G Methodologies for installing RCDs in residential, industrial, and commercial situations, single-phase and three-phase. Residential installations: S/NZS 3000 requires 30 mA RCDs on all final subcircuits, including lighting and socket outlets. RCBOs are now preferred because they avoid losing all lighting when one circuit trips. Commercial installations often require discrimination, ensuring only the closest RCD trips. This may involve using selective S-type RCDs, delayed RCDs, or splitting loads across circuits. Industrial installations: more complex loads, such as motors, drives, and three-phase equipment, may require RCDs with higher surge immunity, adjustable sensitivity, or Type B detection for DC components. Three-phase circuits must use 4-pole RCDs that disconnect all live conductors, including neutral. 13.2H Understand and apply the principles relating to protection for safety in S/NZS 3000 and the role RCDs play in protection for additional safety in damp situations. S/NZS 3000 requires RCDs wherever people are likely to be exposed to shock hazards. Damp situations, such as bathrooms, laundries, pools, outdoor areas, washdown areas, or any place where water reduces body resistance, require RCD protection because the human body resistance is lower when wet. Faults become more dangerous. Leakage current flows more easily. RCDs help ensure automatic disconnection of supply before shock becomes dangerous. 13.2I Understand and apply the requirements of S/NZS 3000 regarding RCD installation and the use of RCDs with handheld electrical appliances. S/NZS 3000 requires 30 mA RCDs for almost all final subcircuits in homes. Handheld appliances in commercial and industrial workplaces must be RCD protected because the risk of shock increases when tools are held in the hand or used in damp or conductive environments. Tools such as grinders, drills, saws, and site equipment must be powered through RCD protected circuits or PRCDs. 13.2J Understand considerations of installing 10 mA RCDs for protecting areas of increased risk in children. 10 mA RCDs provide very sensitive protection. They are used in locations where even small leakage currents are dangerous, such as early childhood centers, schools, medical treatment areas, disabled care facilities, equipment used by or near children. AS/NZS 3000 recommends 10 mA RCDs where children may directly contact equipment or where additional shock protection is required. 13.2 K testing RCDs to ensure compliance with Regulation 24. Testing includes 1. Visual check. Confirm it is type A or better and correctly installed. 2. Test button. Confirms the mechanical action only, not enough for compliance. 3. Full RCD tester verification. O must not trip at half times rated current. O must trip within 300 milliseconds at rated current, 30 mA. O must trip within 40 milliseconds at 5 times rated current, 150 mA. O must trip at both 0 degrees and 180 degrees test angles. If any requirement fails, the RCD is electrically unsafe and must be replaced. 13.3 Isolating transformers. 13.3 Describe the basic operating principle of an isolating transformer. An isolating transformer has a primary winding and a secondary winding, with no electrical connection between them. The only link is the magnetic field in the transformer core. Because the secondary winding floats, meaning it is not connected to earth, touching one conductor on the secondary does not complete a circuit back through the human body. This dramatically reduces the risk of electric shock. So in simple terms, an isolating transformer separates the output supply from earth and reduces shock risk by preventing fault current from flowing through a person. 13.3b Explain why an isolating transformer provides maximum safety when used with only one electrical appliance connected. An isolating transformer gives the highest level of protection when supplying only one appliance. Here's why. When only one device is connected, the secondary side is still fully isolated from earth. If a person touches one live conductor, their body does not complete a circuit, so only a tiny, harmless current flows. There is no return path for sustained fault current to flow. But if more than one appliance is connected, a person could touch two different metal parts at different voltages, which recreates a shock path. So for maximum safety, use an isolating transformer with one appliance only. 13.3c Explain why it is necessary, when two or more electrical appliances are connected simultaneously to one isolating transformer, their earth continuity conductors are bonded together at the transformer but must not be earthed. If more than one appliance is connected to an isolating transformer, all exposed metal parts must be kept at the same electrical potential. To achieve this, the earth continuity conductors must be bonded together at the transformer. This ensures all appliance frames sit at the same voltage. That way, if a person touches two appliances, there is no voltage difference across their body. However, this bonding must not be connected to the installation earth. If it were earthed, the isolation effect would be cancelled, and shock risk returns. So the rule is simple. Bond the earths together, but do not connect them to the actual earth. 13.3d Understand that the isolating transformer may be used in conjunction with other approved safeguards for extra protection where considered desirable. In some situations, isolating transformers are not used alone. They can be combined with other protective devices to improve safety, such as RCD protection, double insulated tools, reduced voltage systems, extra physical insulation or barriers, medical-grade isolation systems. This is common in medical treatment areas, laboratories, workshops, or specialist equipment where the risk is higher. So the key message is: isolating transformers can add another layer of electrical protection when combined with other safeguards. 13.3e Explain why transformers are rated in kVA and not watts or kW. Transformers are rated in kVA, which stands for kilovolt amps, not kW. Here's why. Transformers carry voltage and current, but they do not control power factor. Power factor depends on the load, not the transformer. The transformer must be able to handle full voltage and current, regardless of whether the load is resistive, inductive, or capacitive. kVAR includes the total current times voltage without considering power factor. kW only measures useful power, not the total load on the transformer windings. So the simple spoken reason. Transformers are rated in kVAR because they must carry the total current and voltage, no matter what the power factor is. Bringing it all together. To bring everything together, Topic 13 has shown us how important electrical protection is for keeping people, equipment, and property safe. In 13.1, we learned why excess current is dangerous and how protective devices prevent fires, equipment damage, and cable overheating. We looked at the difference between close and coarse excess current protection, and we learned a large set of key protection terms such as breaking capacity, discrimination, fusing current, and earth fault loop impedance. We also covered how fuses, MCBs, HRC fuses, cartridge fuses, and overload relays work, and why each type is used for different faults or equipment. In 13.2, we studied RCDs in depth. We looked at how RCDs operate, how they detect leakage current, and why NZ requires Type A RCDs for personal protection. We covered classification, installation methods, and the behavior of RCDs in different applications. We also learned the Regulation 24 performance limits, which tell us when an RCD is electrically unsafe, including the exact trip currents and operating times. We looked at where RCDs must be installed, how they protect people in damp situations, and when 10 mA RCDs are needed for children in high-risk environments. In 13.3, we covered isolating transformers, how they reduce shock risk by separating the supply from earth, and why they offer maximum protection when supplying a single appliance. We looked at bonding requirements when more than one appliance is used and learned that the protective earths must be bonded together but not earthed. Finally, we explained why transformers are rated in kVAR instead of kW. Topic 13 brings together all the fundamental ideas behind electrical protection and builds the foundation for safe electrical practice. Understanding these principles is essential for real-world installations and for passing the electrician theory exam. Summary. Excess current overheats cables and equipment and must be controlled. Close protection trips early and protects against overloads. Coarse protection trips only on large fault currents such as short circuits. Key protection terms include breaking capacity, fusing current, discrimination, tripping factor, utilization category, PSC, sensitivity, and earth fault loop impedance. Fuses, HRC fuses, MCBs, cartridge fuses, and overload relays each protect against different types of faults. RCDs detect leakage current and protect people from electric shock. Type A RCDs are required in NZ because they detect AC and pulsating DC leakage. Regulation 24 sets exact trip currents and times for 10 mA, 30 mA, 100 mA, and 300 mA RCDs. RCDs are used widely in residential, commercial, and industrial installations. 10 mA RCDs are used for children, patient areas, and high-risk situations. Isolating transformers reduce shock risk by separating the output from earth. When multiple appliances are supplied, earths must be bonded together but not earthed. Transformers are rated in kVAR because they carry voltage and current independently of power factor.